Hello student, welcome in a Rose project. This Rose project is conducted by Ray Shikshan Samstha Sadguru Gadge Maharaj College, Karad. Myself is Jagtap PS. My subject is a physics. The top chapter number 6, Superposition of a wave. Lecture number 4, Superposition of a wave. The content of the topic is first, practical determination of end correction. Vibration produced in a string. Law of vibrating string. Sonometer. First to discuss about the practical determination of end correction. An exact method to determine the end correction using two pipes of the same diameter but different length L1 and L2 is follows. There are two ways. First is for a pipe open at both ends and second is for a pipe closed at one end. In discuss about the first case, when V is equal to 2N1L1 is equal to 2N2L2. N1L1 is equal to N2L2. Put this value of L1 is L1 plus 2E is equal to N2 L2 plus 2E. Then final equation we get E is equal to N1 L1 minus N2 L2 divided by 2 N2 minus N1 or N2 L2 minus N1 L1 divided by 2 N1 minus N2. This is the end correction for a pipe open at both the end. In second case, for a pipe closed at one end, then V is equal to 4N1L1 is equal to 4N2L2. Therefore, N1L1 is equal to N2L2. Then corrected length for L1 is L1 plus E is equal to L2 is equal to L2 plus E. Then we get equation L1 plus E is equal to L2 plus E. And E is equal to N1 minus N2 divided by 2 N2 minus N1 or N2 minus N1 divided by 2 N1 minus N2. This is about the practical determination of a end correction. Next point is about the vibration produced in a string. These are the three diagrams for a different mode of vibration for the stretched string. In this first figure, there are one loop and length is lambda divided by 2. And second, in figure B, there is two loops formed and lambda 1 is the wavelength. And figure C, there are three loops are produced. And next, consider a string of length L stretched between two rigid supports. These two rigid supports. The linear density is M and the tension T act on a string due to the stretching. If it is made to vibrate by a plucking or by using the vibrator like a tuning fork, a transfer wave can be produced along the string. When the wave reaches the fixed end of the string, it gets reflected with a change of phase by pi radian. The reflected wave interference with incident wave and the stationary wave are formed along the string. The string vibrates with a different modes of vibration of a stretched string is shown in figure. Next, if the string is stretched between two rigid supports and it pulled at its center, the string vibrates as shown in figure A. It consists of an antinode formed at the center and node at the two ends with one loop formed along its length. If lambda is the wavelength and L is the length of the string, we get this figure for a first mode. In this figure, there are two nodes and one antinodes. Length between string is L and wavelength length is equal to lambda divided by 2. Loop of the wavelength is lambda divided by 2. The length of the loop is lambda divided by 2 is equal to L. Therefore, lambda is equal to 2L. The frequency of vibration of the string N is equal to V divided by lambda, and lambda is equal to 2L and V is equal to root T divided by M. Put this value, we get N is equal to 1 upon 2L under root T divided by M. This is the lowest frequency with which the string can be vibrated. It is the fundamental frequency of vibration or the first hormones. Next, if the string is vibrating by a touching it with a light object and string is plunked at the end midway between one of the segment, the string vibrates as shown in figure B. In this figure, there are two loops are formed and three nodes are formed and two antinodes is formed. If two loops are formed in this mode of the vibration, there is a node at the center of the string and its both end. If lambda 1 is the wavelength of the vibration, the length of the one loop is equal to lambda 1 divided by 2 is equal to L divided by 2. Therefore, lambda 1 is equal to 1. Thus, the frequency of vibration is given as N1 is equal to 1 upon lambda 1. Put this value of 1 upon lambda 1 is a L. Then N1 is equal to root T divided by M. Comparison with the fundamental frequency, we get N1 is equal to 2N. Thus, the frequency of the first overtone and second harmonic is equal to the twice the fundamental frequency. Next is the frequency of the first overtone or the second overtone is equal to twice the fundamental frequency. The string is made to vibrate in such a way that three loops are formed along the string as shown in figure C. If lambda 2 is the wavelength. In this figure, there are the two loops are created and nodes, 5 nodes, 1, 2, 3, 4 nodes and 3 antinodes are created. Here length of the one loop is lambda divided by 2 is equal to L divided by 3. Therefore, lambda 2 is equal to 2L divided by 3. Therefore, the frequency of vibration is N2 is equal to 1 upon lambda 2 under root T divided by M. Therefore, N2 is equal to 3 to lambda into T divided by M. Comparing with fundamental frequency, we get that N2 is equal to 3N. The frequency of second overtone or third harmonic is equal to third the fundamental frequency. The vibration are as 4N, 5N, 6N, etc. Thus, all hormones are present in case of a string, stature string, and frequencies are given by NP is equal to PN. Next point is laws of vibrating string. The fundamental frequency of vibrating string under tension is given by N is equal to 1 upon 2L root T divided by M. For this formula, three laws of vibrating string can be given as follows. There are the first law and is called as the law of length. The fundamental frequency of vibration of the string is an inversely proportional to length of the vibrating string if tension T, mass per unit length are constant. Therefore, fundamental frequency N is directly proportional to 1 upon L if T and M are constant. This is the first statement for the law of length. And second law is the law of tension. The statement for law of tension is the fundamental frequency of vibration of a string is directly proportional to the square root of tension if vibrating length and mass per unit length are constant. N is directly proportional to the square root of tension if L and M are constant. And third law is called as the law of linear density. The fundamental frequency of vibration of the string is inversely proportional to square root of mass per unit length. That means linear density. If the tension and vibrating length of the string are constant, means N is inversely proportional to square root of mass per unit length if T and L are constant. If R is the radius and rho is the density of the material of string, linear density is given as the linear density is equal to mass per unit length is equal to volume per unit length into density, and volume is equal to pi r square L divided by L into rho. N is inversely proportional to square root of mass per unit length. If T and L are constant, we get N is inversely proportional to square root pi r square rho. Therefore, N is inversely proportional to the square root of density and N is inversely proportional to the radius. Thus, the fundamental frequency of vibration of a stretched string is inversely proportional to first radius of the string and the square root of the density of the material of the vibrating string. This is about the laws of first law, second law, and third law. And next point we discuss the sonometer. This is the construction for the sonometer or experimental setup of a sonometer. In this experimental setup, this is the sound box and this is the hook, and A and B is the bridges and R is the paper rider and T is the tuning fork, and this is called as the pulley, and this is the wire A to B. This is the wire and this is the hanger, and hanger in a sliding weight are attached. This is the experimental setup of a sonometer. A sonometer consists of hollow rectangular wooden box is called as the sound box. The sound box is used to make a large mass of air vibrate so that the sound produced by the vibrating string, that means metal wire in this case, get amplified. The same principle is applied in a string instrument such as a violin, guitar, tanpura, etc. There are two bridges P and Q along the width of the box, which can be moved parallel to the length of the box. A metal wire of uniform cross section run along the length of the box over the bridge. It is fixed at one end and its other end pass over the pulley. The hanger with suitable slighted weights can be attached to the end and of wire by changing the weights. The tension in the wire can be varied. The movable bridge us to allows us to change the vibrating length AB of the wire. If the wire is plugged at the point middle between the bridge, the transverse wave are produced in the wire. Stationary wave are produced between the two bridges due to the reflection of transverse wave at the bridges and their super, superposition. Thus, position AB of the wire between the two bridges P and Q is the vibrating length. Wire can also be made to vibrate by holding a vibrating tuning fork near it. The frequency of vibration is then same as that of the tuning fork if this frequency happen to be one of the natural frequency of the wave. Standing wave with a large amplitude are set up in the wire since the two vibrate in a resonance. To identify the resonance, a small piece of paper known as a paper rider R is placed over the wire at point in the middle of the length AB as determined by the position of the bridges P and Q. If the frequency of the tuning fork and of the fundamental mode of vibration of the wire match, this is the adjusting length AB of the wire using the bridges P and Q. The paper rider happen to be at the antinode and flames of the wire. Sonometer can be used to verify the laws of vibrating strings. First, verification of first law of vibrating string. By measuring length of the wire and its mass, the mass per unit length small m of the wire determined. Then the wire is stretched on the figure experimentally set up of a sonometer. The hanger is suspended from its free end. The suitable tension T applied to the wire by placing slided weight on a hanger. The length of the wire L1 vibrates with the same frequency N1 as that of the tuning fork is determined as follows. A light paper rider is placed on the wire midway between the bridges. The tuning fork is set up into vibration by striking on a rubber pad. The stem of tuning fork is held in a contact with the sonometer box by changing distance between the bridge without disturbing paper rider. Frequency of the vibration of the wire is changed. When the frequency of vibration of a wire become exactly equal to the frequency of the tuning fork, the wire vibrates with maximum amplitude and the paper rider is thrown up. In this way, setup of a tuning fork by different frequencies like N1, N2, N3 dash dash are used and corresponding vibrating length of the wire are noted as L1, L2, L3 up to Ln. By keeping the tension constant, we will observe that N1 L1 is equal to N2 L2 is equal to N3 L3 is equal to constant. For constant value of the length tension T and mass per unit length M, therefore N L is equal to constant. That means N is inversely proportional to the length if T and M is constant. Thus, the first law of vibrating string is verified by using the sonometer. Then second, verification of the second law of a vibrating string. The vibrating length L of the given wire of mass per unit length M is kept constant for vibration of the second law by changing the tension. The same length is made to vibrate in unison with different tuning fork of various frequencies. If tension T1, T2, T3 up to dash dash corresponding to frequencies N1, N2, N3 dash dash etc. We will observe that N1 under root T1 is equal to N2 square root T2 is equal to N3 square root T3 is equal to constant or N upon under root T is equal to constant. Therefore, fundamental frequency is directly proportional to square root of tension if L and M are constant. This is the second law of vibration of the string is verified. The verification of third law of vibrating string. For verification of third law of vibrating string, two wires having the different mass per unit length M1 and M2 linear densities are used. The first wire is subjected to suitable tension and made to the vibrate in a unison with a given tuning fork. The vibrating length is noted as a L1 using the same fork. The second wire is made to vibrate under the same tension and the vibrating length L2 is determined. Thus, the frequency of the vibration of the two wires is kept same under the same applied tension T. It is found that L1 square root M1 is equal to L2 square root M2. Therefore, L square root M is equal to constant. But by first law of vibrating string, N is inversely proportional to the L. Therefore, we get that N is inversely proportional to square root of M if T and L are constant. This is the third law of vibrating string. In this way, laws of vibrating string are verified using the sonometer. Thank you.